Hey everybody. Last week we looked at atom structure, neutrons, protons and electrons. If you didn't see that video for whatever reason, follow the link below please. It's only about 9 minutes long. Go back and have a look at it because some of that learning you need for today. At the end of this video there's an instruction about what to do, but suffice to say for the moment I want you to be making some notes based on this, so pause it every now and then, go back and recover things if you need to, just to make sure you're happy with the content. So how do we get our picture of atoms now? How do we know that there's this nuclear model with the nucleus in the centre and the electrons around the outside? Well, it all starts about 2,500 years ago with Democritus and Leucippus, who were two ancient Greek philosophers. They didn't do experiments with chemicals, they did thought experiments. And their main idea was, if you were to take something, doesn't matter what, break it up and keep breaking it up, halving it every time, you'd eventually get to the point that something is so small it becomes unbreakable, indivisible. The Greek word for that, by the way, is atomos. So if you take a stone and keep breaking it up, their theory was you'd get to tiny unbreakable bits of stone called atoms, and they were atoms of stone. It's a good theory and it fits with what we now understand about atoms. The problem was other philosophers couldn't accept this model because there was no way to prove it, and the technology wasn't there to observe atoms or work with chemicals in any way that would prove it. So it didn't get proven properly for about another 2,000 years. Dalton had pretty much the same theory and wanted to take it one step beyond, and he looked at two reactions. He looked at the reactants at the beginning, reacted them, and looked at the products at the end. And he noticed that in any reaction, the mass of the reactants was the same as the mass of the products. What you had at the beginning was exactly the same mass as what you had at the end. And his theory was that these atoms were in fact real, and that you had a specific atom for each element. You can see his original diagram on the right of the screen. Carbon, for example, had its own atom. Hydrogen, sulfur had their own atoms, and his theory was that these atoms could be rearranged, combined and separated when reactions happen. They don't disappear, but they move between each other, joining and separating during the reaction. It became known as the billiard ball model because he viewed these atoms as solid spheres, just like a billiard ball or a snooker ball. And it was useful because it helped explain the idea that masses were conserved. However, it didn't explain things like ions. It wasn't until 1904, so just over 100 years later, that Thomson discovered the electron, using an experiment that worked in a similar way to an old-fashioned TV screen. His theory was that atoms are spheres that contain a positively charged material, and that there were negative electrons inside it, scattered randomly. It was accepted actually quite quickly because it helped explain how ions could form. For example, you could take a neutral ion, and that neutral ion could eventually become a positive ion if you end up removing an electron. If that electron is removed, it will leave an overall positive charge, and so there was a mechanism to explain how ions could be formed. That was the plum pudding model. Now, a little later in 1911, Rutherford did his very important experiment with two key scientists, Geiger and Marsden. His experiment helped him to design the nuclear or planetary model of the atom. That's the one we now understand to have the nucleus in the centre and the electrons are in the outside. Rutherford collected data that supported his theory, and this is how he did it. He took a radioactive source and fired that radioactive source towards a detector. That radioactive source gave off alpha particles. Alpha particles are positively charged particles, and they're pretty much the same as a helium nucleus. The only difference is they're moving very, very quickly. So every time these alpha particles would hit that blue detector, it would flash, meaning you could count them. He fired them at very thin gold foil. Now, if the plum pudding model was correct, i.e. big cloud of positiveness and these negatives baked inside it, these positive alpha particles should pass straight through with no problems at all. Now, it turns out this wasn't what was seen. What ended up being seen was something very, very different. So, Rutherford passed those alpha particles directly through. Alpha particles here are in purple. The little yellow dots are what we now know to be nucleuses, and the dotted bits around the outside are electrons. Rutherford didn't know these existed in this way at this point, but he noticed that most of them were passing through, some were being deflected away, and some were being reflected back in the opposite direction. Now this went against their original theories about the plum pudding model, so it was up to Rutherford, Geiger and Marsden to take these observations and come up with an explanation that would help solve the problem. Let's just summarise those results. As the alpha particles passed through the gold leaf, most passed straight through without being deflected at all. Some were deflected a little bit and others were reflected back, but not very many. Rutherford took those 3 observations and had a separate explanation for each one, and you need to be clear about each observation and how it links to its explanation. Okay, so some passed straight through. That suggested to Rutherford that the atom isn't solid, and that most of it is completely empty space, which links in with last week's learning. He noticed that some were deflected, and that must meant there would be a positive nucleus, because surely only a positive nucleus would deflect or push away or repel a positive alpha particle. These positives in the nucleus, of course, eventually became known as protons, which you knew already, but this is an explanation of how we know they're there. And then finally, the fact that hardly any were reflected. That must mean that the nucleus is very, very small, and because the atoms are still have a mass, then that mass must be squeezed into that very small nucleus, and of course when you have a lot of mass in a small volume, that means it's high density, so the nucleus would be very dense. Pause the video now if you want to and review those, because the explanation linking to the observation is vital in both chemistry and physics. Now, the problem with this is it didn't explain why some atoms were heavier than they were predicted to be. It also didn't explain why some atoms glow when they're hot. Those next 2 explanations came from Bohr and another scientist known by the name of Chadwick. Bohr's theory was that electrons orbit at different distances from the nucleus. If you compare the diagram on the screen now with 2 energy shells to the diagram on the screen from earlier with just 1 energy shell, then we see there is a difference in our theories. This was accepted because atoms could absorb and emit light, and the light they emitted had an energy that was exactly the same as the size of the energy gap between those different shells. Bohr used his theory to make predictions about atoms that had not been seen to glow yet. He then made them glow, and his predictions were seen as correct. He was able to predict the exact colour that different atoms could glow. So it's not until you can make predictions that and that can be proven right that a theory is often seen to be correct. And then finally, Chadwick had discovered neutrons, and when he discovered neutrons, that enabled us to understand why atoms weighed that much more than predicted. For example, carbon has a mass of 12 because there are 6 neutrons and 6 protons. If it wasn't for Chadwick, there would be a mass of 6 difference between what was predicted and what was measured. Chadwick was able to predict the true masses of these atoms. So here's our journey overall, from Democritus through to Chadwick. Democritus basically saw atoms as bits. Dalton saw them as balls. Thomson saw them as a plum pudding. Rutherford came up with the idea of the nucleus. Bohr took it further and said that there is not just orbits, but there are different orbits. And Chadwick took it one step beyond and predicted and discovered the fact that there were neutrons. The dates on there are not important, but it does give you an idea of the timeline here. What is most important for you is understanding the gold foil experiment, understanding the difference between the nuclear model and the plum pudding model.